Hi, welcome to another edition of Linear Algebra. Today we are going to talk about electrical networks. So we will be building on the concept of networks we talked about last time, that was for traffic. Now we are going to look at something more interesting. That's the case of electrical applications. So let's go ahead and take a look at this topic. So item number 4, basic electrical networks and Kirchhoff's laws. We are going to talk about that. So this segment is going to require a bit more terminology and familiarity with basic science issues. Some of you might have seen this thing in high school in your physics classes, or perhaps your introductory physics in university. Let me go ahead, explain some of the concepts, do some of the basic problems today, and next time we are going to do more advanced stuff. So let me just mention some basic ideas. The type of circuits we are going to be talking about are going to be very basic. It's just made out of some batteries, some resistors like this light bulb, of course some wires that connect them, and some switch that turns the current on or off. Essentially no more complicated than your basic flashlight. Okay, so that's what we are going to be looking at. Now if you have a set of batteries and set of light bulbs and they are connected in a variety of ways, the problem actually becomes a bit interesting and challenging. So we are going to start from the very basic situation. Very basic situation. Again, we just have a battery. It provides electrical current to some item like a light bulb, and well, the current goes in a loop and comes back to the other end of the battery. And then we have things to talk about here, which is the amount of voltage that you deal with at any segment of your circuit, the amount of current that is flowing in it, and perhaps the resistors that you have in your circuit. So let's go ahead and become familiar with these concepts. Let's see, what do we have? In its most basic setting, we have a battery. So we have a battery. The battery, well, you are very familiar with the batteries. You've used them all over the place. It has two poles indicated as a positive and negative. Okay, so positive is shown by a long bar and negative sides is shown by a short bar. And then you have some wires. Now we always draw our wires looking like nice looking squares and such. Of course no wire behaves like that, but it's just customary to draw wires like this, as if they make perfect corners and such. And then so we have some wires, and then something on the wire. Typically in the most simplest case we set a light bulb. So we have a light bulb. It's typically shown by this zigzag line indicating that we have a resistor. So a resistor, an example of it would be just a light bulb. And as we said, these wires act in a very idealized way in our drawings. They come in the shape of some squares or rectangles and so on. Okay, we need some basic scientific principles related to this picture. Again, most of you are familiar with this either from your daily usage of it or from a class you might have taken. Well, what's the quantity that's measured related to a battery? Of course, that's going to be the voltage the voltage of the battery is going to be a significant issue for us. Well, what is the unit by which we measure the voltage? Well, the unit is called the volt. Of course, you have 6-volt batteries, 12-volt batteries, and so on and so forth. And the notation for it, of course, is just the letter V. The scientist's name, whose name is being used here, is Volta. So we use the unit volt for that. Okay, the quantity that is related to this is called resistance. Resistance is the unit that we use for measuring it is called ohm. And the notation for it is the capital omega in Greek letters. And of course, when it comes to the wire, the quantity we measure here is the current. The unit in which we measure it is called Amperes. That's a French scientist whose name is attached to this thing. The abbreviation for it is A or AMP for amp. So when you're dealing with your circuit breakers and looking at how many amps it handles, 15, 20 or 60 and such, that is what we're talking about here. Okay, so what's the basic well, let's write this unit was volts. The amount, the voltage itself. Let me erase this thing and write it the right place. The voltage that we measure is shown by V. The current that we measure is shown by I. The resistance that we measure is shown by letter R. So let me color these three things. And we are going to have so-called Ohm's law, part of Kirchhoff's laws, that says the following, that the voltage is equal to the resistance times the current. If you use the stronger battery here and the same resistor, then the amount of current that's going to be flowing through is going to be that much more. If you use a high resistor but with the same battery as before, then the amount of current that's going to flow here is going to be less. So we have this one, voltage is equal to resistance times the current, and that is one of the Ohm's laws. Next issue that we have to pay attention to for a more complicated circuit is something we already saw in the segment on network analysis. Well, in network we had a set of roads and arches and so on that connected the flow to each other. Here we can have a similar situation. So if you have a wire and a second wire attached to each other and then the third wire coming out, and if you assign a current I1 coming in here and I2 coming into this node and a certain current I3 flowing out of this, then at that node we have to have incoming is equal to the outgoing. So that's not going to be very hard to agree with, that we have a node law, sum of incoming is equal to sum of outgoing. Now I'm going to keep the problem at that simple level. I'm just going to solve some problems that are not going to give us any kind of difficulty, and later on we are going to go ahead and look at some more detailed issue. Let me just again bring a bit of pictures and the history of this topic, and then we are going to come back and do some problems. So we said we are looking at the most basic of all the circuits you can imagine, just like your basic flashlight. So here I have a battery. I can control, by the way, here you can go to FET simulations to play with the same thing. You can increase the voltage of the battery. You see it's kind of indicating the current becoming faster, and there is presumably more light coming out of this. So we have a control on our batteries. That main control is through the voltage of the battery. As I increase the voltage here, you notice our voltmeter here is reading a larger number. We have another measurement here. That's the current that is going through the wire. The current is measured by amperes. So here again, as you notice, as I increase the voltage, then correspondingly the current is going to go higher up. I have a resistance in my circuit. The resistance can be changed too. If I increase the resistance here, you see the current comes down to a crawl, but if I reduce it, then the current becomes, as you notice here, stronger. So you see the current went up. So that is the basic, and again we are just looking at that, just that setup. Now sometimes to understand the situation with these electrical currents, they make a parallel to what you might have in your backyard with a pump and a hose and such. So if you have a pump and you're pumping water through a hose, and perhaps there is some obstruction in that hose, anything like say sand or anything, you will have pressure dropping across that obstruction until it comes back, and then you have a cycle here. That is a situation that's somewhat similar to what happens in our circuits. So sometimes you might benefit by thinking about the water flowing through some tubes as opposed to the current going through some wires. Okay, the scientist we talked about, we said the resistor is, the resistor is measured in terms of ohms. Ohm was a German scientist. Then the current was measured in the unit of amperes. Is a French mathematician by name of Ampere who was working on electricity and magnetism. His name attached to that. Our batteries are measured in terms of volt. That's in honor of the Italian physicist Alessandro Volta. And of these people, one of them is magnificently recognized on Eiffel Tower. That is the French. The Eiffel Tower was celebrated in France, of course, and the name of 72 scientists, French scientists, appears on it, and that includes the person responsible for the unit amperes. Okay, so that is for a little bit of history lesson, if you wish. Now we go back to our usual problem setup and see what is it that we are going to be handling here. So let's start with a very simple setup. So suppose I have a battery. Let's say this is a battery. So we said the unit of battery is measured in terms of volts, and then don't get fooled by this square looking wires. Just for the sake of drawing, they do it like that. Nothing happening at these corners, just drawn like that. Then we have anything that uses that electricity or creates a blockage to the electricity and such. So let's suppose this is a resistance of 2 ohms. So maybe I write the whole name, 10 volts, 2 ohms, and the wire, we have to complete the circuit for something to happen, otherwise nothing going to go on. So typically you see a switch sometimes drawn somewhere to indicate that you can turn this thing off and on. And then a current is going to flow through this thing. We said that current is going to be measured in amperes, or just amp, or just A. And the voltage is equal to the resistance times the current. So this is going to be 10 volts, and the resistance is 2, and the current, well, the current here turns out to be 10 over 2, and that is 5. So you can abbreviate to amp, or just write 5A, or however you like it. Okay, so that's a very basic problem. Now, one issue here that is a bit more complicated than the one in the network analysis last time we looked at is the issue of the direction of the current. It's a bit of a sticky issue, direction of current. Well, when you have people or cars going through a road, you see which way they're going, so that nobody is confused as to who's going which way. But when it came to electricity flowing through wires, people didn't really know what is flowing, what's causing it, and so on. Of course, they had experimented with batteries. They knew something happening with this configuration of the batteries. It creates something, and then you can let that something, whatever it is, to flow. So they had the designation of various substances they could use in their batteries, and they had the designation of who they want to consider positive and who they want to consider as a negative side of the battery. Then came up the issue of what is it that is flowing. This is like several centuries ago. People didn't have a notion of atomic nature of matter. They didn't know what it is made of. So they assumed something is just flowing. They didn't know quite what. They assumed it's going from the positive side to the negative side. So that was the conventional view of the current. So they assumed something is moving from the positive side to the negative side. And that went on until the beginning of the 20th century, where people realized the atomic nature, and they realized that for most substances like wires, copper wires and such, what's happening and what is moving is flow of electron currents that's going from negative side to the positive side. So starting with the 20th century, electron flow or electron current became a dominant point of view. Okay, and then the textbooks fall into two categories. Some of them just go with the old conventional format, some of them with the new format. It doesn't really matter for us which one you pick. They could be considered equivalent to each other. So what we choose is that the direction of the current for us is going from the positive side of the battery to the negative side. So you can imagine positive things flowing in this direction. It's the same as imagining that the negative particles are traveling in the opposite direction. Okay, that's item number one. Now this issue of positive and negative is going to become a little bit more complicated later on, when we don't actually know which way the current is supposed to go, but let's hold that until next time that we look at some more complicated problem. Okay, this is all great. What does it have to do with linear algebra? You might be wondering. Okay, some basic physical laws here and there. But how do you make linear systems out of it? Well, very simple. If you make a complicated circuit, it immediately gives rise to a set of equations. You'll be lucky if they are just linear equations. So with this type of instrumentation, we get the very simple laws because of the two laws that we have. This is essentially node law. Then we have a second Kirchhoff's law that we are going to include that, and I'll talk about that in the context of a problem now, and then we are going to formalize it next time when we introduce a bit more complicated ideas here. Okay, so let's go ahead make a supposedly complicated circuit. So complicated circuit means you have a bunch of batteries, a bunch of resistances, all sort of wires and nodes and so on. So here is a standard type of situation. Suppose I have a battery and then I have some resistance, means a light bulb, and then some other resistance, and then perhaps still another resistance here, and I go back where I came from, and then I can have another one of these loops, again some other resistance, some other battery. So now is a complication. I have a second battery, then I can come and if you wish, I'll make another resistance here and go back to this location. Okay, now as examples go, this is kind of a simple example because this battery and this battery, we have the positive sides of it attached to each other as opposed to they being opposite orientation. So it's easy to think that some current is going to come here. So some current is going to come. Let's call it current number 1. And then similarly here, some current is going to come and flow. Well, let's call that current number 2. They come at this node, so we might as well label our nodes, say call it node A and this one node B, and the two currents are going to join forces and they follow into this bridge looking element here. Let's call this current number 3, and well, they enter this and then split again, so this goes up and goes back to the battery here, and same way here, this thing is going to come, let me redraw this thing so I don't create a misunderstanding. So we have this one. Now one thing we need to pay attention to is that when you go from a node to another node, you might have several branches or roads available to you. In any of them, you have the same current from beginning to end. So this yellow, of course, you don't see any reason for the current to change, but here is a bit more challenging situation to think about. From A to B, but going on that green branch, the current is the same from one end to the other end. So this current here is going to be same as the current over there. And the same issue in this one. In this blue branch, also the current is same thing from beginning to end. So if you're designating this one to be I2, this one should be designated I2 as well. And of course this I3 is applying all the way from beginning to the end of this yellow current, yellow branch, and that at the end of it is going to be I3. Okay, so we have these nodes, and then from node to node we might have several branches available. On each of them there is a single current that applies from beginning to the end of that branch. Okay, that's one observation. The other observation is the node law, exactly same as before, that whatever is coming in has to be equal to whatever is going out. So if you want to go ahead at branch at node A, who's coming in, I1 and I2 are coming in, and outgoing I3. So this is what is coming in, and this is what's coming out of that node. In B, you exactly have the same thing, but who's in and who's out is they're reversing their positions. What's coming into the B is I3. What's going out of the B is I1 and I2. Of course, these two equations are the same thing, even though physically we're thinking about them as different items. But as we had in the case of the network analysis, always one of our node laws is redundant, and it's mathematically speaking same as what the rest of them are going to say. Okay, that's for the simple issue of the node laws. Node laws doesn't cause any problem. Now coming to Kirchhoff's law, or more advanced version of the Ohm's law. If you had one voltage in one resistor and one current, the situation is simple as we wrote it here. But if you have multiple voltages, multiple resistors, and so on, we have to adopt some strategy to handle this, and the strategy is referred to as Kirchhoff's law. So let's see, make sure I have the spelling of his name correct. I had to look up how to, what is it? Kirchhoff, double F. Okay, I'm going to postpone the detailed explanation of this thing to next time. Most of the problems that you're going to encounter, you can handle it with a simple observation that we are going to have here. So let's designate some strength to our batteries and our resistances. So let's go ahead, and I'm going to call them by some say this is battery with voltage V1. This is maybe I just put some numbers. Say this is 10 volts, and say this is 20 volts, and let's make these numbers to be all different. So suppose this is 2, 3, 4. These were of course measured with unit of ohms, 2, 3, 4, and let's say this is 5 and 6. That's good enough. Now we are going to use the concept of a loop. So I'm going to loop around until I go back to where I started from. You can start from any point on the loop and complete the loop and come back. It doesn't matter where you start. Let's start here, for example. So I'm going to call this thing loop number 1. So going on loop number 1, the idea of Kirchhoff is that if you go and measure changes in voltages and add them up, so your voltage sometimes goes up, sometimes goes down depending on what you're going across, the algebraic sum of all those voltage changes has to be 0. So how does this go? As we go from negative side of a battery to positive side of a battery, we gain our voltage. So I write plus 10. So as I started from this point, and I'm going to loop like this across the battery, I'm gaining 10 volts, and then I'm going to spend them. I'm going to spend them first across this resistance of 2 ohms. By Ohm's law, the voltage that I'm going to lose here is going to be 2 times whatever the current happens to be. I don't know what the current is, but I know the resistance is 2. I say 2 times I1. That's what I spend here. That's how much I lose here. Then my voltage drops across this one, the 3 ohms resistance. How much is going to be lost here? Well, it depends what current is supposed to go through that, and that's going to be 3 times I3. So minus 3 times I3. So remember Ohm's law, which was here's Ohm's law. The voltage across any resistance is proportional to the resistance and the current. So we multiply those two in each segment. So in this segment, we come back to the current of I1. My resistor is 4 ohms. So I write minus 4, and the current is I1. And I have come back, and then the sum of all of these things is equal to 0. So if you go through a loop and come back to where you were, you have this balance equation. You can of course write it in more intelligent ways, 6I1 plus 3I3. So you can simplify it to 6I1 plus 3I3 is equal to 10 if you wish. Well, you come here and make another loop. So I come here, make a loop like this. Again, you can start from anywhere and go in any direction, but let's make it kind of standard. So I start from this point, and I'm gonna go gain 20 volts when I go from negative to positive side of this in the looping direction. If I go from negative to positive, I go up that much voltage, and then I start to spend it across these light bulbs or resistances, whatever I have. So here I'm going to spend minus 5I2, and then in the middle is same as before, minus 3I3, and then this one again same current I2, and minus 6I2 is being spent over there, and that's equal to 0. So of course you can clean that up as well. So, of course you get 5 and 6 looks like 11I2, and then we have of course 3I3 as before, that's equal to 20. So let's write our equations. I have 6I1 plus 3, let me write it nicely, plus 3I3 is equal to 10, and the other one is 11I2 plus 3I3 is equal to 20. Well, I have 3 variables I don't know, I1, I2, I3. I have 2 equations. Where is my other equation, huh? Do you see the other equation? Other equations, of course, your node law. Yeah, if you want to write it here, or this node A or node B, so one of them is redundant. You don't need both of them. If you put an extra one, well, when you solve your equation, you're going to see that they cancel each other out. You get a row of zeros, but here if I write I1 plus I2 minus I3 equal to 0. Okay, so a system of 3 equations in 3 unknowns. So I'm going to solve this thing. How am I going to solve it? Well, thankfully we have that little software that's going to it's going to save us a bit of time in doing this. So, but before we go there, just let's see what happened. We have nodes. From a node to another node, On any of the branches, same current applies. As we go on these things, we choose a point and then loop around a loop and write an algebraic sum. As we go across a battery from negative to positive in the direction of the looping that we go, we add the strength of the battery. That's how much voltage we are gaining, we say. Then we are going to have voltage drops across each of the resistances that we have. Voltage drops are proportional to the current and the resistance. We write all of them throughout the loop until we get back to where we were. That total sum is going to be 0. We rearrange it. Then we can write another loop here for the bottom here. Some of you might say, well, I want to write a loop all the way going across. Yes, you could. Ends up being essentially sum of these two equations. Those steps that you were taking with the Gaussian elimination. Same thing shows up here physically. If you want to choose some other loops, you're free to do so. You just get linear combination of equations you already have. Okay. Now we have an equation. We go ahead and solve it, and the issue is what is I1, what's I2, what is I3. Okay. Let's go ahead and do that quickly. So we had our lifesaver here was Gale. So let's go ahead and edit this thing. I have a 3 by 4 equation. My numbers were 1, 1, -1 and 0. Then I had 6 and 0 and 3 and 10. Then I had 0, 11, 3 and 20. I hope I wrote everything correctly. Is that right? Okay, let's hope so. Now resume. So we said this is a pivot. Click on that. We want to eliminate this one. Well, it eliminated. Now, good thing is to convert everything into a leading one. The way you do it is click on the edge block, and that makes your pivot to be 1. Then I use this pivot to eliminate the item below. The numbers we had chosen were not like any friendly numbers, so you see peculiar numbers showing up. Now you have a choice of eliminating these things or eliminating from the bottom. Let's this time emphasize the more efficient style when you're doing hand calculations. So I came here, made my 1, then I use this as a pivot, eliminate this entry, use this as a pivot, eliminate that entry, use this as a pivot, eliminate that entry. These denominators 117, it might make more sense to also have this one in the same denominator. Of course you have to multiply this by 3. It becomes 150 over 117, or just leave it as it is. So I have my answers 80 over 117, 50 over 39, and 230 over 117. Okay. So we took the pain of these problems away by giving you this software, and here is our final answer. This is 80 117 as 50 over 39 if you want to write it like the other ones, and this is 230 over 117. Almost, this is almost 2, so this is like 2 amps. This is less than an amp. The problem is essentially done. We have found I1, I2, I3, and we have the current in each of the resistances here. Okay, what is left? What's left is sometimes the problems present us with bigger challenges. One of the basic experiments that you guys going to do in your circuit analysis classes is something very standard, referred to a Wheatstone bridge. Or maybe you had it in high school. So it's a setup for measuring resistances and such. It's actual device that you're gonna play with. Uh, Maybe you want to search it online and look at the device. So it's some sort of current. We have here some battery, and then we have one resistance, some connection point here, another resistance, and then it connects to the other side of the battery, and then we have another one of these things, and we have a bridge element here between these two branches. So some currents are specified, some resistances and voltages are specified. So for example, this one in your textbook, this is 10 volts, this is 1 ohms, this is 2, this is 2, this is 1, and this one designated as being 2 ohms. The question is, we want to figure out what is the current in any of these segments. So as we said before, there is going to be a current flowing here, split into these two branches, and then collect back here and come back to the battery. Well, what is challenging here is at these points it's not quite clear